Section 1.2, solutions of a differential equation. Now that we know a little bit about differential equation, so this question is, how does the solution of a differential equation look like? Well, it turns out by definition, the solution of a differential equation is a function, y of x. By the way, it can be constant, which at least has is n times differentiable. That means the nth derivative of it exists on an open interval I is called the solution of an ODE, ordinary differential equation. If the function itself and all its derivatives satisfies the differential equation. So the solution is a function which can be constant. It's a function of x, which its derivatives and itself must satisfy the equation. So the question here is verify, that means determine for all constants c1, c2, y of x equals c1 sine of x plus c2 cosine of x is a different solution to this second order differential equation, y double prime. Okay, to determine if this guy is a solution for that differential equation, so because it has two derivatives, so we start with the solution, right? And we take two derivatives of this guy. So this would be c1 cosine of x minus c2 sine of x. And y double prime is minus c1x minus c2 cosine of x. So I'm going to call these guys equations 2. I'm going to call these equations 1. Remember, all these equations came from the solutions. We're trying to verify. That means show this guy satisfies this differential equation. So I'm going to replace the y double prime with minus c1 sine of x minus c2 cosine of x. And then I'm going to add y itself, which is c1 sine of x, c2 cosine of x. Question is, does that add up to 0 according to the equation? Yes, these guys cancel, so does these guys. 0 is equal to 0. Yes, this guy is the solution of the differential equation, of this differential equation. For any C1 and C2, regardless of what the constants are, this combination happens to be the solution of the second order ODE. Sometimes the solution shows up in this form. Okay, notice y is not on one side and we cannot solve for y. Turns out this is called what? Implicit form, whereas that guy is explicit form. So we will get to that in a minute. So the bottom line is I cannot solve this for y. So what I'm going to do is use what? To verify this is the solution of this differential equation. I'm going to use implicit differentiation. Implicit differentiation. What does that mean? That means I'm going to take this solution, which was given to me, and notice c is a constant, and take the derivative as I go from left to right, one at a time. Notice this is a product of two functions, so I have to use product rule. Derivative of the first is 1 times the second. Derivative of the second is 2y prime times x, plus derivative of 2y is 2y prime. Derivative of x is 1, derivative of constant is 0. Remember, c is constant, meaning any fixed real number. Okay, so now I'm going to try to factor out y prime. As a matter of fact, 2y prime. So I'm going to get what? Yx plus 1. Move the 1 over. Move this guy over. Then I'm going to divide both sides by what? Xy plus 1. Okay, like so. And then these guys cancel. So I get what? Y prime is equal to what? 1 minus y squared divided by 2 times xy plus 1. And that's exactly what we were supposed to show. So therefore, yes, this is indeed the solution of that differential equation. Once again, the fact that the solution here had y on one side, everything else on the other side with no y in it. So this is called explicit solution. All right, explicit. The solution is in explicit form, I should say. So explicit form, not solution, but explicit form, correct? And this guy, the second equation, the second solution here, even though if you can factor out the y, but there is no way I can isolate the y and write it on one side of the equation. So this form is called implicit form of the solution. So explicit, y is on one side, everything else on the other side, just like this guy. Implicit, even though y's are on one side, but you cannot isolate this equation for y. Even if you factor out the y, you're still gonna have what? Xy plus 2 inside the parentheses. So that's the difference between the forms. All right, of all the differential equations, basically we are interested at this point of the semester with so-called linear differential equations. The definition of linear differential equations happens to be right here. So in other words, you have a function of x times what? The nth derivative of y, some other function of x to the n minus first derivative all the way to some coefficient function of x times y equals some function of x on the right side. Notice all these coefficients, y0, a0, all the way to an, including f of x on the right side, they are a function of x only. And it's called linear differential equation of order n, or sometimes people call it nth order linear ODE. So that's the title of this equation inside the box. Question, is this linear? Yes, it is, because it fits the description. So in this case, a sub 0 is 1. Remember, these coefficients are functions, but functions can be constant. As a matter of fact, they can be 0 as well. A sub 1 is x squared. A2 is what? Sine of x, and f of x is e to the x. So this precisely fits the description of the linearity by definition of what linear differential equation is. Incidentally, because the highest power of y is derivative of y is 2, so this would be second order linear equation, correct? What about this guy? Yes, you have triple y triple. So a sub 0 is x, a sub 1 is 4x squared, and a sub what? Excuse me, guys. A sub 1 is missing because there is no what? Y double prime, so this guy is missing. That's okay. A sub 2 is 4x squared, and a sub 3 is negative 2 over 1 plus x squared, and f of x is missing, so no problem, right? Absolutely no problem. Sometimes some of the coefficients are 0, sometimes even the function on the right side is 0, and sometimes the coefficients are constant, so no problem. Here, a sub 0 is what? 1, because the coefficient is 1. There is no third derivative. Second derivative is what? The coefficient is 3. And first derivative is missing, and the function itself is missing, and the function on the right side is e to the x plus 1. So this is the coefficient of fourth derivative, third derivative, second derivative, first derivative, the coefficient of the y, and the external function on the right side. Here, a sub 0 is 1, a sub 1 is negative 3, a sub 2 is negative 40, and there is no f of x on the right side. So I don't know if you notice, sometimes on the right side we have a function, okay, sometimes we have a 0. If we have 0 on the right side, these type of functions are called homogeneous. Homogeneous. If the function on the right side, like this example, remember it was e to the x, it wasn't 0. So these guys are called non-homogeneous functions, non-homogeneous. So these are linear homogeneous, these are non-linear homogeneous. Okay, so let's solve some problems, see if we can go from differential equation and to the function itself. So this is y triple prime, okay? So I need to really be good at what? Taking integrals. So techniques of integration are highly recommended. Okay, to go from y double prime to triple prime to y double prime, I have to take the integral of both sides, of course, with respect to x. So what do I get? I get y double prime equals what? 3x squared plus constant, c1. Why do I have subscript? Because I'm going to have more constants in a minute, so I can't possibly call it all c. Okay, to go from second derivative to first derivative, I need to take the antiderivative of this expression. So I get x cubed plus c1x plus 1 more c. Notice even though you get a c on the left side, that's okay. You can always move that c to the right side and combine it with this guy, which still is a constant. So to go from y prime to y, I need to take antiderivative of this guy with respect to x. So y is equal to what? Oh, it is what? Let's see what we got. Here we have x to the what? 4 over 4 plus c1x squared over 2 plus c2x plus what? c 3. Do you see it? So notice what we have here is called general solution. Why do we call this general solution? Because it has constants in it. So you have infinite many solutions. Do you see it? So let's just double check here. So this guy is what? 3x squared plus c. So that guy is x cubed plus c1x plus what? c2. Is that right? And this guy is what? X to the 4 over 4 plus c1x squared over 2 plus c2x plus c3. The next example is solve the same equation, except now it's subject to initial conditions. Notice if all the conditions are based on the same values of x, so these are called IVP problems, initial value problems, okay? Initial value problems. Why do we have these conditions for? So these are conditions to find C1, C2, C3. Okay, so in previous example, we found out this guy is the general solution. Why do we call it general solution? Because what? You have constants in the solution. But now, the minute they give you what? Conditions, then you get to find the C's. So here it says y is equal to 1 when x's are equal to 0. So that just tells us what? C3 is equal to 1. Here it says when you take the derivative of the solution you came up with and replace the x's with 0, y prime should be -1. So I'm going to take the derivative. So that would be like what? X cubed. And this would be like c1x. That would be like c2. So now I'm going to what? Replace the y prime with -1 and what? X's with 0. And what do you know? C2 is -2. Now, according to this condition, y double prime at 0 is equal to 4. So I'm going to take one more derivative. So that would be like 3x squared plus c1 from here. And then I'm going to impose the condition. So y double prime is 4 according to the condition when x's are 0. So what does that tell us? C1 is equal to 4. So therefore, the solution is x to the 4 over 4 plus what? 4 over 2, which is 2x squared, minus x plus 1. So this should be the final answer. However, notice the difference between general solution and this solution is general solution had constants in it. This solution has no constant, so it's called particular solution, okay, or specific solution. And by the way, it's unique. That means it's one of a kind. Yes, this guy consists of infinite many solutions, but the minute you impose the conditions, guess what? The answer is one of a kind. How would you check this out and to see if it's okay? Well, take 3 derivatives of this, see if it's 6x, and then apply the initial conditions to y, and then first derivative and second derivative, see if it satisfies the initial condition. If it does, so you're good to go. Do you see it? I hope it's correct. So this guy is y double prime is equal to e to the negative x. So to go from y double prime to y prime, I take the antiderivative of e to the negative x. So the final answer is what? Negative e to the negative x plus what? C1. Now to go from y prime to y, I need to take the antiderivative of this guy with respect to x. So that would be like e to the negative x plus c1x plus c2. Is that right? So this is equal to y. So this is called general solution right there. So now I have to, in the next problem, they said, okay, solve this. So this would be like find a general solution, which I did. In the next problem, it says, no, solve this, but subject to these initial conditions. But notice in this particular problem, the values of x inside the parentheses are different. So this would be called what? Boundary value problems. So why? Because you have conditions imposed on different values of x. So it's BVP, boundary value problems, versus IVP, initial value problems. So now we found out the general solution is what? E to the negative x plus c1x plus c2. Now let's apply the conditions. Well, y is 1 when x is 0. Is that right? So remember, e to the 0 is 1, so c2 is 0. Is that right? So now I'm going to take don't have to take derivative because the conditions are based on the function itself, the solution itself. But this time I'm supposed to replace the y with 0, x's with 1. So I get this. But remember, c2 came up to 0. So therefore, c1 is minus e to the negative 1, which is minus 1 over e. Therefore, the particular solution is e to the negative x plus c1x, which is minus 1 over ex, plus c2, which was 0. So this is so-called particular solution. Do you see it? And it has to satisfy the condition. It has to satisfy the differential equation. In other words, if you take the derivative of this guy twice, you should get e to the negative x, and it also has to satisfy these equations. So one of the things I hope you notice is the number of constants, the c's, in a general solution of ODE, and the number of conditions, initial conditions, in an initial value or boundary value problem solely depends on the order of the differential equation. What does that mean? That means if you have the order of differential equation was 3, so you had 3 conditions, and then you had 3 c's in the general solution. Here, the order of differential equation was 2, so you had 2 c's, and in the next follow-up problem, in order to find c's, they had to give me 2 conditions. So the number of c's and the conditions solely depends on the order of differential equation. Question, are these equations linear or not? Well, the first guy looks like it's linear because a sub 0 is 1. Excuse me. A sub 1 is what? Excuse me. I meant to say it is not linear. Why is not linear? Because what? Y has appeared as an exponent. Notice this guy messed this up. So yes, the answer is not a linear ODE because y cannot appear as an exponent. So this is not a linear equation. This guy is not a linear equation either because y prime cannot have a power. This guy is not a linear equation because what? Y cannot be argument of a trig function, nor it can appear what? As an exponent. So this is not a linear function. What about this guy? No, it's not because what? Y triple prime cannot appear at the bottom of a fraction. What about this guy? Well, this guy needs a little bit of a simplification like so. So if I put the xy over on the other side and kind of factor out what? Y, I'm going to end up with something like this. Do you see it? So that would be sine of xy minus xy. So is this linear? Well, it sure looks like it. Why? Because a sub 0 is 1. A sub 2 is 0 because what? Y, excuse me guys, a sub 2 is 4, correct? Sorry about that, is 4, correct? And what? A sub 3 is 0 because there is no y prime. And a sub 4 is sine of x minus x, which is a function of x. And capital F of x on the right side is tan of x, which is a function of x. Remember, all these coefficients, including the function on the right side, must be a function of x. Is the last one linear? Yes, it is, because a sub 0 is 1. A sub 1 is 0, so is what? So a sub 2 is 3. A sub 1 is 0 because there is no triple prime. And second derivative has a coefficient. First derivative is missing. So is the function itself. But capital F of x, the external force on the right side, is x. Notice all these coefficients, they have to be function of x. They could be 0 or constants. It's a-okay. So looks to me, this guy is linear. As a matter of fact, it's third order. And this guy is also linear. As a matter of fact, it's what? Fourth order. Do you see it? Finally, later we will learn in the course that when the coefficients of the linear differential equation happens to be constants. Do you all see it? Constants. And the equation is homogeneous. The solution of these type of equations happens to be in this form. We will learn this in upcoming chapters. Y equals e to the power of rx, where r is a real number. So r is any real number. So the idea is not to solve this equation, but find all values of the constant r such that this guy is a solution to this what? Second order linear homogeneous differential equation. So let me write that down. Y double prime plus 2y prime minus 3y equals 0. It's called second order linear homogeneous what? ODE. So when you have linear homogeneous equations where the constants happens to be what? Where the coefficients are constants and the external force or the function on the right side is 0, the solution should look like this. Y is equal to e to the rx. Question is, can you find values of r such that this will be a solution to this differential equation? Sure. Because the claim is this is a solution, so itself and its derivatives should satisfy this equation. So I'm going to take a derivative. Remember, r is constant. So if you take one more derivative, because the highest derivative is 2, I get r squared e to the power of x. So this is equation 2, this is equation 1. So now let's substitute 2 into 1 and see what we get. Well, this would be like r squared e to the rx plus 2 times r e to the rx minus 3 times e to the rx equals 0. You see it. So now, if I factor out a common factor, which is e to the rx, I get r squared plus 2r minus 3 is equal to 0. So according to the, zero factor product, either e to the rx is 0 or r squared plus 2r minus 3 had to be 0 in order for this product to be 0. You and I, we both know exponential functions can never be equal to 0 for any r or x. So therefore, the only hope is to solve this guy for r. So if you factor this guy out, so you get 3, 1 plus minus, okay? So either r is equal to 1 or r is equal to negative 3, meaning the solutions to this particular, the functions, these are called fundamental solutions, happens to be e to the x or e to the negative x. And later we will find out the general solution is a linear combination of these. That means you multiply this guy by a scalar, and then you multiply the second guy by a different scalar, add them up, and that constitutes the general solution. You all see it. We'll talk about this much later in the course, perhaps like in chapter 3. Thank you.